Yeah, thanks a lot. So yeah, hi, I'm Cornelius, and yeah, EFTfitter, tool for combining and interpreting measurements. And yeah, even though it's called EFTfitter, it's not only for EFTs, but yeah, I will mention that in a second. So the idea basically is pretty much the same as Oliver introduced, and it's also EFTfitter is basically a kind of interface to BAT.jl. But the situation you're in is basically that you have a model, and that has, of course, some free parameters, and then you have some measurements, and measurement usually has uncertainties and most likely also some correlations. And sometimes you measure different observables and they all depend on the same parameter. And then you want to basically compare or combine these measurements and combine your observables. And that is, here's one example where we did this. So this is combining B and top quark measurements. And what you see here is basically the posterior phase space, and this is a 2D projection. And you can see the 90% credible intervals, and you can see that, for example, combining the gray B physics and the light blue top physics results in a combination that is much smaller. And in this case, you have really some kind of orthogonal constraints. Okay, so now why is this tool called EFTfitter? So what are EFTs? Let's start with that maybe. So EFTs are a concept that are now quite prominently used in LHC physics, because we saw that with our current machine, we didn't find any direct observations of BSM physics. So we can ask ourselves what happens if the BSM particles live at an energy scale that is much higher and way out of reach from our current machines. And then we can basically do an effective parameterization of the standard model, and we can add higher order terms. These are the higher dimensional operators, and then they have some kind of coupling strength. These are these Wilson coefficients C. So this is basically just an effective theory, and you want to constrain these coefficients C. And if they are not zero, that might hint at some BSM physics. And also this package is grown historically, and we released the first EFTfitter package in 2016 when this EFT gained popularity, and this was then still based on the C++ version of BAT. And we wanted it to be targeted for these EFT interpretations, because that is what we used it for. And since we now have this nice rewrite of BAT in Julia, we also wanted to rewrite the EFTfitter tool on top of BAT basically. And there were some discussions about the naming of this tool, but since we still wanted to focus on this EFT community, we kept this name for now. But let's see if we might change this, because what I'll show you now is that this is more generally applicable, what it does. So as I already mentioned, what is EFTfitter? It basically just does a statistical combination and interpretation of your measurements, and it is well suited for this EFT stuff, but not restricted to that. And you can combine measurements of the same or even of different observables. Of course, we use a Bayesian approach because we rely on BAT.jl. And as a result, we usually want to get the posterior distribution of our parameters. And what we also focus on in this tool is that we try to have a correct treatment of uncertainties and correlations. And the idea is that we allow the user to implement its own model, so its EFT model, for example, and we can also handle constraints on the observable values and on the parameters, of course. And but in the end, as I already said, it's just some kind of hopefully user-friendly interface to BAT.jl for a very specific kind of likelihood. And it's maybe also the same slogan that Johannes used, so it's nothing too fancy, but hopefully at least a bit helpful for some people. So okay, let's maybe take a look a bit more in detail how this works. So on the one hand side of your likelihood, you of course need some measurements. And for EFTfitter, you just need the nominal values and the uncertainties, and if available, also the correlations between these uncertainties. And on the other side, then you need your model. And with a model, what we mean here is that you basically have a function that describes the dependency of your observable on your model parameters. And then you put this into EFTfitter, and this builds the likelihood, and then the likelihood is basically directly passed to BAT.jl, where you then can choose the priors and then use all of these nice algorithms that Oliver introduced for doing your posterior exploration. Then what you get out are posterior distributions for your parameters, and this is then what gives you these constraints that I showed you on the very first slide. So if we talk about combining measurements, the most accurate combination of different measurements would of course be possible if you have access to the full likelihood, and then build a common likelihood function. But in high energy physics especially, that is not so easy, because usually to access the likelihood, you need access to information that is not publicly available. So usually only inside the collaborations, and even then it's not even very simple, because inside the collaborations they use different frameworks and so on. So that is often a bit tricky. So yeah, also a little advertisement for the talk tomorrow that is on this HS3 standard, which tries to improve this problem. But yeah, for now it might be helpful to have some approximative approaches for combining measurements in a much simpler way. That is what we do in EFTfitter. We just have a rather minimal set of information that is usually published, like the nominal values, uncertainties, and so on. And then we have only one assumption, that is that the measurements are Gaussian. So that we basically have a nominal value and Gaussian uncertainties. And on that basis, we then have the thorough statistical treatment. And so EFTfitter cannot give you the most accurate combination in all cases. But I mean, you can do combinations without access to the likelihood, and this can, for example, help you to estimate where to look, so which processes are of interest, for example, or also studying what might be the influence of correlations. All right, so that is basically what Oliver introduced you, so how Bayesian inference works. And yeah, the one assumption is that we have Gaussian measurements, so we have mu and sigma, and in the multivariate case, of course, you know how a multivariate normal distribution looks like, but I just wanted to remind you, because that is what the EFTfitter likelihood looks like, and that is all. It's basically a multivariate Gaussian. So what we do is we sum over all our measurements. So these are the x's, and basically what we do is we calculate the distance between x and y is our prediction for the observable. So y as a function of these lambdas are our parameters, and y is then the prediction. And then we have, of course, some covariance metrics in it. And as an example, we would, for example, measure different cross sections, and they depend on different Wilson coefficients, and then we can do predictions for how this cross section would vary as a function of this Wilson coefficient. So that is what we do. And yeah, very important is, of course, this covariance metrics, and that is what you can then input. So in principle, you give your uncertainties and also correlations, and this is then converted into the covariance metrics. And in EFTfitter, you can give multiple terms for this covariance metrics, because usually you have different categories of uncertainties, like you have statistical and systematic, or you can even break down all your systematic uncertainties and so on. So this is then basically the likelihood function that is constructed. And in the very simple case where you only have one observable and you want to combine multiple measurements of the same observable, this comes down to being basically the same as the blue method. So the best linear unbiased estimator, which some of you might have heard about. Right. So now you might think, okay, this is just Gaussians, and combining Gaussians, what can go wrong, right? So this will all look very Gaussian. But the point is that because we have these our models, so the dependence of our observables on the model parameters, this can be arbitrarily complicated, right? So this is just what you as a user put in. And this means that the posterior distribution that comes out does not need to be Gaussian. So here's one example where we did combination of cross sections and W helicity fractions, and the cross sections usually have a quadratic dependency on these EFT Wilson coefficients, and for the W helicity fractions there are some analytical calculations possible, and I mean there's not too complicated, but then in the end the result can look quite strange, and this is just a 2D projection of I think 5-dimensional phase space. So not everything is Gaussian then in the end. So this is why we need to rely on efficient samplers to do the posterior exploration. Okay, so the question is now, how do I include my model in EFTfitter? And this is quite simple. So it's just you need to implement a Julia function that gets in your parameters and that returns a number, basically. And if you do, for example, EFTfits, then of course the question is, how do I get my dependence of the cross section on these Wilson coefficients. And then there's usually quite a chain of tools. So usually you start having some mud graph simulations of this process as a function of these Wilson coefficients, and because that is slow, because it's Monte Carlo simulation, you basically then do some kind of interpolation through this, and this then in the end you just have a quadratic interpolation, which you can then put into this function, or as I said, for the W helicities, there's some analytical formula that you can simply put into the function. So I would now just like to show you one quick example of where we used EFTfitter. So this is basically, it's the same example I showed you before, combination of top quark measurements from Atlas and some B measurements. And we got our model. So this is for the top quark. This is this quadratic dependency, for which we used mudgraph and then interpolation. And then for the B physics, we used tools like Flavio, and then matching and running between different EFT theories. So also a lot of theory involved. But in the end, it's just the function returning a value, and then we implemented this into EFTfitter, and then what comes out is distributions like that. So in this case, we have something like 60 different measurements of 40 different observables, also some distributions included. And this is also quite nicely showing again that for this physics case, like combining top quark and B observables is quite helpful, because they have these orthogonal sensitivities to the parameter space, and then combining them really improves your constraints on these parameters. So we did this in up to, I think, 14 dimensions or so. So a 40-dimensional fit, right? So one more example is on a study where we showed that the correlations between your uncertainties might matter. So here we have a combination of again, this top quark cross sections and W helicities, and we got these measurement values and uncertainties from the publication, so from Atlas, for example. And the problem is usually there's no or not much information given on the correlation between these observables, and so we tried to do some kind of best guess. So we looked at these observables, and we looked at their systematics, and we tried to think which of them might be correlated, and then we just assumed slighter or stronger correlations, and then built this 55 times 55 correlation matrix, having some assumptions in there. And then we just put this in and compared this to the no correlation scenario, and then you can see that this does have an impact. And if you expect uncertainties on the order of the Halloumi LHC, then this might become even more important. So correlations are also something that should not be neglected when combining measurements. However, we often don't have access to these correlations, so that is why you can also treat correlations as a nuisance parameter in your fit using EFTfitter. So then the correlation coefficient is basically a free parameter of your model. The problem is just that your correlation matrix, of course, grows quadratically with your measurements, so you can only do this for a very small number of correlation coefficients. Otherwise, your fit won't converge anymore, because it's basically just unconstrained nuisance parameters. So yeah, that is also why we hope that the collaborations provide in the future even more information on the correlations, or at least to those that they have access to. So for example, if you have bin distributions, you usually have bin-to-bin correlations that should be published. All right, so I showed you that before, so now maybe let's take a quick look at how the EFTfitter API looks for the user. So as the very first step, you basically just define your parameters and priors. Since we do the Bayesian thingy, that is just BAT.jl syntax. So in this case, we have two coefficients, C1 and C2. One is just a uniform, and the other has a normal distribution as a prior. And then you need to implement your model, and this is just any Julia function that gets this basically named tuple that has the same structure as this parameters that you defined. Actually, I just noticed I'm inconsequent. So this C1 and P1, so C1 should be P1 and C2 should be P2. Of course, And yeah, basically that is where you put in your info or your information about your models that you got from Monte Carlo simulation or whatever. So you can have a function chain there and running a lot of stuff in the background, but in the end, it should just return one value. And then you also need to specify your measurements. So for that, you have this measurement object that gets a function. And this, if you only give a function, it automatically assumes that it's an observable that is unconstrained, but you can also convert this first into an observable that then gets this function, then gets some physical minimum and maximum values. And so then the second argument is just the nominal value that is measured for this for this observable. And then you can specify different types of uncertainties. So they are just given as a named tuple. And you can just say whether you want to have this measurement active in this combination or not. And there's also some convenience functions for having bin measurements, so like distributions. Then you can pass in vectors of these numbers, and internally it will then be converted back to so the bins are converted to individual observables, so to say. Right. So one new feature that we have now is that you can not only return a single number from your prediction, but a tuple of numbers for when the second value is then also some kind of model uncertainty. So where basically the value of this uncertainty depends on the current set of your parameters. Right. So this is then also added to the diagonal of the covariance matrix. And yeah, speaking about covariances, so the last part is that you need to specify the correlations for all of your uncertainties that are included. So for example, you can say there's no correlation, then it will build the I matrix of the correct size for you. You can give explicit correlation matrices, like passing a matrix into that. There's a convenience function where you can just build your own correlation matrix, because for example, having this 55 times 55 matrix, that's a lot of entries you need to type in. So you can just, for example, say, I know the correlation for this one type of uncertainty between measurement 1 and measurement 2 is that correlation coefficient. And also you can access the individual bins of your distribution, even though you didn't specify any names for that. Or you can even pass block matrices into this to this full matrix. So if you have, for example, access to the block matrix for this distribution, for example. Okay, so then so what you then just do is you build an EFTfitter model from these parameters, measurements, and correlations. And so this is just some pseudocode of how it looks internally. It's basically this is just a wrapper for the user. So it's still just named tuples in there. And the only thing that is done when constructing this model is that only the active measurements are considered, and only the active types of uncertainties are included. And then the covariance matrix is built correspondingly. So removing all these rows and columns that are not needed anymore. And in the second step, then you build a posterior measure. So that is how we do this in BAT now from your model. And in that step, then some more efficient representation of your input is built. So this is then still called density. I don't know if Oliver likes that, but and that's how it is currently. And this is then just the vectors of your floats and for the measured values and so on. So this is hopefully then more performant. And so now the newest version of EFTfitter then does some kind of dispatch on, for example, if you have nuisance correlations or if you have model uncertainties, your covariance matrix changes for each set of parameters. So you need to invert your covariance matrix each time. So that is what is done here if you have a varying covariance matrix. But if it doesn't, in the most simple case, you have a fixed covariance matrix. So you can do this inversion once and store this. So there's then the point where we dispatch on different implementations of this likelihood function that hopefully makes this code performant. So, and then, we basically have our posterior distribution. We plug this into BAT, choose some kind of sampling algorithm, and just run BAT sample, and then we get out these samples, and we can plot these. And what we often do is we look at these like 90% intervals to use them to constrain or to get constraints, right? So one last thing I would like to mention is that sometimes you might wonder, what is the impact of my different measurements on this combination? And there's one feature implemented here that basically you remove one measurement from your combination and then just see how much or how much your constraints get worse, basically. So in this example, we just removed from this combination this Atlas F0 measurement. So there's basically not much change. But then if you remove this Atlas TT bar measurement, you see that your constraints get worse. And basically based on how worse your results get by removing one of your measurements, you can build some kind of ranking based on the size of these intervals, basically. There are some caveats, of course, because an outlier measurement will lead to yielding better constraints if you just remove this. But just to get some kind of feeling, because in this blue methods there are some weights assigned to the measurements for the combination, and we wanted to have something similar. Right. So my last slide now is what's up next with the EFTfitter. So there's now version 0.2 since this morning, actually, and it's now these model uncertainties are included that I showed you already. It's now also possible to assign weights to your observables. That's actually nothing you would want to do if you do really combinations of your measurements, but there are people using EFTfitter to do tuning of Monte Carlo generators, and there it seems to be quite common to use different weights for your observables. So they needed that feature, and some smaller improvements to this user interface and to the internal structure with this multiple dispatch now to speed up the computations. And further plans in the future is that we also want to consider including some mechanisms to include limits, because often you have like 95% confidence level limits on a process that have not yet been observed, but they might also give you some sensitivity to your parameters. This would then mean that you need to add non-Gaussian terms to this likelihood function. I was also thinking about doing or having an interface or a template for doing simple curve fits, because essentially the likelihood function is the same like for a least square fit in some cases. So that is also what you could use the tool for, doing a Bayesian least square fit, so to say. And we had discussions about rebranding this tool, because as you might have seen, it's not very focused on EFT users, but we wanted to keep this for those that are used to that, but maybe we can now make this or give it another name and make this more generally applicable. So if you want to check out EFTfitter, here's the link to the GitHub repository, and of course your feedback is very, very welcome. And if you don't know how to get started, there's of course a tutorial, but there's also a little hands-on example here in the slides where you can basically try to reproduce these two plots. So everything you need for that is given here. So these are basically the measurements and uncertainties, and there's some numerical descriptions of your observables with, I guess, too many decimal points, but it doesn't matter. So there you can also just launch Binder or Google Colab if you don't want to install it in your environment, and then you can basically try to reproduce something that looks similar to that. So with that, thanks a lot for your attention.